that is C OH on left side like this. And its structure, yes, actually in biomolecules writing structure is an enjoyment. Oh, you can also enjoy this by writing in your notes. This is structure, and just you have to remember whether we are considering all the carbons completely or not. This is 1, 2, 3, 4, 5, 6. Now, actually, this alpha form, which is of having 111 degrees of angle of specific rotation, when dissolved in water, simply that cyclic acetal just open like this. Then again it will come back. And if you recall your carbonyl compound chapter, say acetals or ketols, cyclic, that is nothing but semi-acetals and semi-ketols on hydrolysis give back their original parent carbonyl compound. Is it not? So this is cyclic semi-acetal. When it is hydrolyzed, when it is dissolved or kept in water, immediately it will open up to give its original compound. But immediately it will attack again. That is the structure in that attack. When say for example beta form attacked by this OH is there. Now it is released, and again when it is coming to attack, this may be attacking on the same side or on the other side. In that course, automatically it may turn back to beta form, or in the other direction if OH attacks, it may convert into alpha form. Possibility is there. Like this, among these three, there is an equilibrium established. And just you remember, in this equilibrium, these two are having some sort of existence. It is very less time, very less concentrated open form. Very less concentration of open form is observed. And now why there is meta-rotation? Let me give. When it is alpha form, which is of having 111 degrees of, no, sorry, it is, the data is given reverse. This is alpha D glucose, which is attacked, and here I am changing the structure. Dear students, just you observe, beta structure is written here. Alpha should possess OH on this side, and this should possess hydrogen. Hydrogen. Okay, let me make this like this. Here, one change is happened. It is alpha. And now coming to this beta. Beta, it should possess OH on this side, not on the. This is hydrogen, H, OH. Okay. The structure, that is representation, is given a different one. No doubt at all. Alpha form is having all these characters and beta form is having all these characters. Only while writing, the structure is given. Alpha, beta is given alpha structure and alpha is given beta structure. No problem at all. Now I think already in for the last few minutes we are discussing, and in the previous class also. So just you correct it. Now, when this alpha, which is of having 111 degrees of angle, dissolve, open, and now it may convert into alpha back or it may convert into beta. An equilibrium is established. Here, very less concentrated open structure is formed. Clear? Now, at equilibrium, what happens? If it is started from this, coming into this and establish an equilibrium, at equilibrium, this alpha D of the mixer at equilibrium is established at plus 52.5 degrees. Very interesting and important. Now, when it is started with alpha dissolved in water, because of establishing an equilibrium, this is slowly changed and it is of retained. It becomes constant at plus 52.5 degrees. And if you remember equilibrium chapter condition, For a given reaction which is establishing an equilibrium, the equilibrium state can be reached from either side. Is it not? So when alpha is dissolved, equilibrium is established, the alpha D of mix is appeared at 52.5 degrees. Instead of alpha, if we are dissolving beta D glucose in water, which is of having specific rotation 19.2 degrees, again it is also open close. In due course it is establishing an equilibrium in this scenario. So again with plus 19.22, the specific rotation changes to plus 52.5. That means what we are saying, what we are observing here, whether an alpha form of alpha D glucose is dissolved in water or beta D glucose is dissolved in water, the specific rotation after dissolving in water changes from the respective specific rotations to a constant value of 52.5 degrees. Clear? And with this mixed alpha D, we can calculate the percentage of alpha and beta form that can exist in this solution. How? Let me give the formula. Here, alpha D mix, that is nothing but 52.5 degrees alpha D mix is equal to, we know alpha form is 111 degrees into X percent. Just imagine that alpha form is X in percentage, and then plus beta form. Beta form has 19.2 specific rotation into, now when X percentage is alpha, what is the percentage of beta? Only when two are present? Yes, it is nothing but 100 minus X percentage by 100. That will give this X and 100 minus X. With this formula, that is, again you observe here, this is mixture average of alpha and beta forms. Now if we are imagining that alpha form is X percent, automatically beta will be 100 minus X percent, because percent is per 100. And now when these are the percent, now alpha specific rotation 111 into X plus 19.2 into 100 minus X by 100 is equal to this one. On solving, you can find X. And just you remember, for your convenience sake, I am giving the information regarding this. Alpha form is around 36%. And beta form, you can calculate, you can find X and value. Once you are getting X, the other one is 100 minus X. Beta form is found to be 64% approximately with fractions. This is the value. In case if you are interested to add the values, you can go. Alpha and beta forms that exist in equilibrium when either of these two are dissolved in water is 36 alpha and 64 beta form approximately. In case if you require the accurate value, you can calculate. Got the idea? That is about mutarotation and the reason for mutarotation. Just it is nothing but actually glucose is not existing in open chain. It is existing in cyclic semi-estable condition. That cyclic semi-estable condition exists in two forms. One is alpha, the other one is beta. Alpha is with specific rotation of 111 degrees. Beta is with specific rotation of 19.2 degrees. Now, when either of these two are dissolved in water, they are establishing an equilibrium among these three: alpha, open chain, beta form; beta, open chain, alpha form. In due course, when it is establishing an equilibrium, a fixed proportion of alpha and beta forms are there, and with that one, the mixture is getting a different optical specific rotation, that is 52.5 degrees. Clear? The reason for mutarotation is converting alpha into equilibrium or beta into equilibrium mixture. Now the question, the other questions. That is nothing but when it is having aldehyde group, when it is responding with yes, Tollens reagent and failing solution, why this glucose is not responding with sodium bisulfite and ammonia and Schiff bases? The reason is simple. Actually, this open chain can only respond to Tollens reagent because aldehyde can only respond to Tollens and failing carbonatic solution, but not esterols or ketones. So this can respond with a Tollens reagent, failing solution and Benedict solution. Clear? But it fails to respond with a Schiff's reagent and ammonia and sodium bisulfite. The reason is simple. When we are discussing about this equilibrium, it is very less stable and very less concentration is formed in open, which is sufficient to respond with these three reagents. Very important point. The open form of glucose, open chain form of glucose is of having very less concentration in equilibrium because it is highly unstable. Immediately it has to convert into alpha or beta form. So in that conversion, just fraction of time it will exist in open form. That fraction of time with that less concentration is sufficient to react with these three. But that concentration is not sufficient for these three to react. Yes, some reagents can react even with very minute concentrations, whereas some other reactant or reagents they require some optimum concentration of that particular substrate. Then only they can respond. Here, these three require optimum concentration that is not achieved at any time by this equilibrium, and hence these are not responding with these solutions. But they can respond with this because we even minute quantities sufficient to respond with these three reactions. I think now you got the idea, clear idea about this. Clear? Like that, these are the structures given. Now, coming to the next topic, that is nothing but Havard structures of glucose. Havard structure. It is nothing but the name is scientist. And what are these Havard structures? For that purpose, again, just let us keenly observe this alpha and beta form of glucose. Just here I am taking alpha form. Alpha D glucose. You can also go through this structure once. It is like this. CH2 OH and the remaining 1, 2, 3, 4 carbons OH on this, not on this. This OH is attacked. That's why it is in now in semi-ester, cyclic semi-ester condition. And then OH, H, H, OH and OH, H. Here, this is nothing but C1, C2, C3, C4, C5. Here hydrogen is there and it is out of this. Now, if you observe, this one is existing in a cyclic form. You observe that one. In that cycle, 1, 2, 3, 4, 5 carbons are there, 1 oxygen is there. That means it is a semi-acetal. Cyclic semi-acetal. Structure of this glucose has 6-membered ring. 6-membered ring where 5 carbon atoms plus 1 oxygen atom present. And there is one organic compound with these 5 carbons and 1 oxygen atom. If you remember the cyclic ethers. Yes, what is that? It is nothing but O. This is the structure. Can you recall? Yes, it is pyron. Pyron, a six-membered ring with 5 carbons, 1 oxygen. And now, when glucose with this semi-stall condition or structure is of having similar to this structure, and hence glucose structure is known as pyranose structure. Pyranose. This is its structure is known as pyranose structure because it is very close to similar to pyron. In its ring, 6-membered ring with 5 carbons, 1 oxygen. That's why glucose structure is pyranose structure. And in this pyranose structure, this Hawat is trying to give the positions of this OH group. And you know what is the structure represented here? Even though it is cyclic form, when it is in straight chain we are writing. Can you recall what is this projection? Yes, it is Fisher projection. This Fisher projection, about this Fisher projection already we discussed in optical isomerism. Is it not? Just once one term is introduced to you in any class, you have to remember it forever. And when we discussed about the optical isomers, different representations in projections, Fisher projection and flying wedge projections, and then Sahar's projections, Newman projections, all these we discussed. So out of that, this is Fisher projection. This Fisher projected structure has been given in cyclic form, which is similar to that of pyron, and hence pyranose structure. And in this pyranose structure, Hawat tried to give the positions of this OH and H groups. Just you remember, in the next page I will write that Hawat structures, but before that you remember, in Fisher projections, when we are giving pyranose structure, 6-membered ring, or that 6-membered ring is supposed to be in plane. All these 6 members in plane. In Fisher projection, the right side, all the groups which are present on right side are supposed to be below the plane of that ring. And the groups, yes, already you got it. The groups on left side are supposed to be on above the plane of the ring. Again I am repeating, in Fisher projection, the groups on respect to carbons which are present on right side are represented in below the ring structure in Hawat structures. And whereas the groups which are present on the left side are represented above the ring, above the plane of the ring in Hawat structures. Clear? With this information, let us write the Hawat structures for alpha and beta forms of glucose. Let me start with it. This is alpha D glucose in Fisher projection, fourth carbon, third carbon, second carbon, and this is first carbon here after converting into semi-acetal. Here hydrogen, and just you remember, here I have to make you to remember this hydrogen is said to be on right side. It seemed to be on left side on fifth carbon, but here the computation, that is the orientation, is related to this hydrogen and this hydrogen. Here let me write that, this hydrogen and this CH2OH group, these two in that condition, because it is three-dimensional arrangement actually, but here what we are writing in 2 dimensions. So for that purpose I am making you to remember this. Hydrogen is supposed to be on right side. Why it is said? Because just now we discussed in Fisher projection all the groups which are present on right side are represented below the ring. That is the reason forever in D configurations you remember H is on right side. That should be below the ring. So this is alpha D glucose. And in Havard structure, where pyranose structure is given, it is written like this. O, this is 5 carbons, 1, 2, 3, 4, 5, 1 oxygen. Huh. In pyron, double bonds are there, but in glucose there are no double bonds. But that's why it is not pyron structure, pyranose, similar to that of pyron. The similarity is only in number of members, that is number of atoms in the ring, and those atoms, how many carbon, how many oxygen. 6-membered ring, 5 carbons, 1 oxygen. That is the only comparison, not double bonds. Clear? So this is pyranose. Now in this case, the first carbon is this one. 1, this is 2, 3, 4, 5. Now let us write the structures. Here, right side on first carbon, OH on right side, hence OH down, H up. On the second carbon also, where OH is on right side, and hence here OH, here H. But on third carbon, what happens? H is below, because in right side OH is above. And on fourth carbon, OH is below and hydrogen is above. And now coming to this, that is the reason why I ask you to remember. Hydrogen is on right side. That means where it can be? Yes, it is below here. You can remember that CH2OH is like fraction. Always. Now 1, 2, 3, 4, 5. This is sixth carbon. Sixth carbon is always above the ring. This is Havard structure of alpha D glucose. Now coming to beta D glucose, where OH is on left side on first carbon. All the remaining is as it is similar to that of alpha D glucose. Here also again you remember this hydrogen is supposed to be present on right side. It is on right side, always on right side, you remember. And the remaining, here fourth carbon, OH and H. Third carbon, H, OH. And second carbon, OH, H. Now 1, 2, 3, 4, 5, 6 carbons. Now what is its structure? For this purpose, this is the structure given. First of all, pyron structure like this, 5 carbons, 1 oxygen. Then the orientations. If you observe, this is the first carbon, and here OH is on left side, hydrogen is on right side. Hence hydrogen here, OH here. And then in the second carbon, OH below, H above. On third, H below, OH above. And on fourth, again OH below, H above. On fifth, what we have to write? S. Just you remember, it is fraction. Like this. OH. Now, if you observe, these two forms differ at first carbon, where on first carbon, OH is present below the ring in alpha D glucose, whereas in this case OH is present above the ring in beta D glucose. Just only at C1 they differ, and hence these two are animals. I think you got thorough idea about the structure of glucose. First of all, from experimental result, we established open chain structure given by Bayer. And thereafter, this open chain structure is giving results with different reagents, but with some reagents like sodium bisulfite, Schiff's reagent, it is not responding. And there is a peculiar phenomenon called mutar rotation is observed. And for when we are searching for this, it is observed that this glucose, not only glucose, any carbohydrate is not existing only in single form. And even it is not existing in open chain form. It is existing in cyclic semi-estol or ketol forms. And during that cyclic hemi-estol or ketol orientation or ketol formation, the configuration at C1 is differed for each carbohydrate. So based on that configuration difference at C1, the two forms of the carbohydrates are considered as alpha and beta forms. And in this class, we completed the discussion on alpha and beta forms of glucose. And now, the meter rotation, the answer for meter rotation is established because alpha D glucose has 111 degrees of specific rotation, beta D glucose has plus 19.2 degrees of specific rotation. Even though they are having independently different specific rotation, once either of these two when dissolved in water, they are establishing an equilibrium among the three forms alpha form, beta form, and open chain. And in that establishing the equilibrium at particular concentration or proportions of alpha and beta forms are establishing an equilibrium with the open chain, and either direction, that is whether we are starting from alpha or from beta, the same composition as per equilibrium condition, there it is found to have plus 52.5. And then we calculated the alpha and beta glucose percentages also. Then how these alpha and beta form structures can be. For that purpose, Howard proposed a new structure phenomena by comparing with the iron. Only in having the cyclic structure which has 6 membered, out of those 6 members, 5 are carbons, 1 is oxygen. So that's why the structure given to glucose is known as pyranose structure. And in that pyranose structure, when we are writing the structure from Fischer projection, all the groups which are present on the right side in Fischer projection are present below the ring, and all those groups which are present on left side are above the ring. Thereafter, the result appears like this. Clear? And dear students, you be thorough with this glucose. In the next class, we are going to write the remaining monosaccharide structures like fructose, mannose, allose, and then galactose. Simply because they are epimers. One is only fructose is functional isomer. The remaining three are epimers. Just by changing my change at that particular carbon where configuration different, we can write the structure. Thereafter, these monosaccharides will combine to give disaccharides. We are having in our syllabus three disaccharides. One is nothing but maltose, and before that, yes, it is sucrose, then maltose and lactose. Thereafter, we are having three polysaccharides also. They are nothing but starch, cellulose, and yes, glycogen. All these structures in single class we are going to complete in the next class, and for that purpose you should be thorough with these alpha and beta forms of glucose. I always take the structure of glucose as the standard structure, and how the other structures are arrived from this always I will compare with that one. So for that comparison to understand, you should be thorough with this one. Clear?